In this three-part tutorial, we're going to look at forces and how they affect an object's motion. Forces are simply pushes or pulls that objects exert on one another. You can probably think of a lot of examples of forces in your everyday life. These might include, for instance, gravity, an electrical force, frictional forces, normal forces. By the way, the word normal force refers to the force that prevents, for example, one surface from physically passing through another surface. So for example, when you put your hand on a tabletop, your hand doesn't physically pass right through the tabletop. Why not? Because the tabletop exerts a normal force on your hand, preventing it from going through. So there are lots of different types of forces. And the key idea that we're going to be exploring in these tutorials is the notion that a net force on an object will affect or change its motion. A net force here simply means that, for instance, imagine if I had an object and there were two forces on it, but they balanced each other out. In that case, there'd be no net force and the object's motion wouldn't be affected. So we're going to consider cases where there is some net force on an object and determine how it affects the object's motion. So let me start you out with a warm-up question. Let's imagine that you're watching the motion of a particle through space. And here it is following along this path. What's shown is a snapshot of the particle's position at equally spaced moments in time. So each dot, for example, might represent where the particle is 1 second later. If you look at this, what evidence do you see that there is some net force acting on this particle? What I'd like you to do is pause the video right here and spend a moment or two thinking about this. We'll return to this question in a few moments. Let's now look at the general question about how forces affect motion. And I want to go through some key concepts that you'll need to know. The first concept: a net force will cause an object's velocity to change. That's what forces do. They cause the object's velocity. And when I say velocity, I mean the speed and or the direction that the object's traveling in. So if there's a net force acting on an object, that means the object's velocity, namely speed and or direction, is going to change. As a corollary of this, we can say that if there is no net force on an object, then the object's speed and direction won't change. In other words, the object will, if it's moving, it will continue to move in a straight line with constant speed. So here's a depiction of an object traveling along to the right. You're seeing its position at different equally spaced moments in time, and you see that the object's traveling in a straight line and it's traveling at constant speed. So as long as there's no net force on an object, objects naturally travel in straight lines at constant speeds. You don't need a force to kind of keep it going. This is what objects naturally do. If there's an object which is initially at rest and there's no net force on the object, then the object is going to remain at rest. So again, both of these things are simply saying that a net force on an object will change the speed or direction of the object, and if there is no net force, the object's speed isn't going to change, and whatever direction it's currently moving in, that won't change either. A little bit of terminology. Anytime an object's velocity changes, we say that the object is accelerating. Formally, we define acceleration to be the rate of change of velocity. So if you're taking a calculus-based physics class, we can write this as the acceleration vector is equal to the rate of change of the velocity. So this is what we mean by the acceleration is the rate of change of velocity. Mathematically, it's the derivative of the velocity. If you're not in a calculus-based physics class, that's okay. Just think of it as follows. Anytime the velocity of an object changes, in other words, its speed changes, or its direction changes, or both of them are simultaneously changing, in either case, we say the object is accelerating. So this first concept here is basically saying that a force on an object will cause it to accelerate. Now let's go to the second key concept. Suppose I have an object, there's the particle, and it's moving initially with some velocity v0 to the right. And then I apply a force F to it in the same direction that it's moving. So the object's initially moving to the right, and I'm pushing on it to the right. What's going to happen? The object will speed up. It's still going to move to the right, but it's going to go faster and faster and faster. So when you push on an object in the same direction that it's already moving, it simply speeds up. Here's another picture of that. So here's the object, and I'm pushing on it with the force F to the right, and you see how the object is going faster and faster and faster. A third key concept is that if I have an object, and let's say here's a particle and it's originally moving to the right with some speed v0. So here's a particle moving quickly to the right at speed v0. Now suppose I apply a force to it that's in the opposite direction that it's moving in. Then the force is going to cause it to slow down. The object is still going to move in a straight line, but the force is going to cause it to slow down. Here's a picture of that. So here's the particle, initially moving, it's moving quite fast to the right, but because there's a leftward force on it, the particle's motion to the right is slowing down. See, here's its velocity v1 at a later time. At a later time, it's moving at speed v2. You see how it's slowing down. It's still moving in a straight line, but slowing down. So again, this third concept simply says that if you have an object moving and you push opposite to the way it's moving, the particle slows down. Perhaps not surprising. The fourth key concept is slightly more subtle. This says that if the net force on an object is perpendicular to the direction it's moving, so it's not in the same direction that it's moving, it's not opposite to the direction that it's moving, it's perpendicular to the direction the object's moving, then what will happen is that the object it's going to change its direction. So here's an example. Here's a particle moving with some initial speed v0 to the right. And if I push on it in a perpendicular fashion, and when I say push on it perpendicularly, what's going to happen is that this particle's path is going to bend and it's going to start curving. What I want you to imagine that is that we always readjust the direction of the force so that it always remains perpendicular to the object's motion. Okay? So if we do that, then the object's direction is going to change, but its speed will remain constant. It will not change. So perpendicular forces alter the direction of the particle, but they don't affect how fast it's moving. So in this first example here, when we had a particle initially moving to the right, but there was a perpendicular force to it, what will happen is that perpendicular force will cause the path to bend. The particle's still going to be moving at the same speed as before, but it's going along a curved path. Now when it's here, it's currently moving in this direction. But if there's a perpendicular force on it, then the path is going to continue to get bent, and it will get to here. And if we continue to apply a perpendicular force, it will get bent some more. So perpendicular forces bend the path. Let's look at this example here. Here's a particle moving to the right with initial speed v0. If there was no force on it, it would just continue to move to the right at that same speed. But because there's a perpendicular force, the particle is going to follow this bent path. It's going to bend like this. It's going to be moving at the same speed, still v0, but along a bent path. Now when it's here, it's currently moving in this direction. But if there's a perpendicular force on it, that force is going to bend its path and bend its path. So to summarize, when an object's moving, if the force is in the same direction that it's moving, it goes faster. If the force is opposite to the direction it's moving, it goes slower. If it's perpendicular to the motion, it doesn't go faster or slower. It remains the same speed, but its path will change. It will bend. So now let me ask you a follow-up question. We've just seen what happens when a force is parallel to the motion, when it's opposite to the motion, and when it's perpendicular to the motion. But what happens if a force is applied which isn't either of these things? In other words, suppose I have a particle, here it is, it's initially moving along to the right with some speed v0. But suppose I apply a force like this. This force is not parallel to the motion, it's not in the same direction as the motion, it's not opposite to the motion, neither is it purely perpendicular to the motion. It's kind of somewhere in between. How is this particle going to respond? Here's another example. The particle is moving to the right here initially, but there's a force pointing kind of sort of up and to the left. How is that force going to affect this particle's motion? Well, the way to think about it, let's go back to this case, is as follows. When we're applying a force like this, it's kind of like part of the force is along the direction the particle's moving, and part of it is perpendicular. In particular, if I imagine breaking up this force vector into two components, this force is made up of a piece, a component that's along the direction of motion, and a piece that's perpendicular. So this piece of the force is going to cause the object to speed up. But this perpendicular piece of the force is going to cause the object's path to bend. So the net direction of this particle is going to be something as follows. It's going to move sort of like this. It's going to move to the right and upwards at the same time, and it's going to be gaining speed because this part of the force makes it go faster and this part makes it bend upwards. So the particle, rather than going along a straight line like this, will in fact follow sort of a curved path like that. Let's return to this case. Here the particle's moving to the right. Now you see how this force is kind of pushing to the left? So that's going to slow it down, but it's also slightly pushing upwards, perpendicular to the motion, so that's going to bend it. So if I look at this force vector, I can think of it as being made up of a horizontal piece and a vertical piece. This piece, which is opposite to the motion, we've seen that when you apply a force opposite to the motion, it slows it down. So this part of the force is going to cause it to slow down, but this part of the force is perpendicular to the motion, so it's going to cause it to bend. So what's going to happen is the particle, rather than just moving along to the right, it's going to slow down but bend upwards at the same time. Once again, this particle, as it moves, this force here is going to cause the particle to slow down. So its rightward motion is going to slow down, but it's also going to bend upwards, kind of like this. There's a common thread that's linking the concepts that we've gone over so far. In particular, we've seen that when you apply a force to an object, it affects its motion. It changes its speed, could speed it up or slow it down, or it changes its direction, or both. A key idea is that the direction in which the object's velocity changes is determined by the net force on the object. In other words, the object's acceleration is always in the same direction as the net force on the object. Remember, an object's acceleration means that its velocity is changing. That's what acceleration is. So the change in the velocity of an object is always in the same direction as the net force. So let me show you, illustrate what this means with a simple picture here. Suppose I have a particle, here it is, and it's initially moving to the right with a velocity v naught. Now, suppose I push on it with a force to the right. We've already seen that that's going to cause the object to speed up. It's still going to travel to the right, its direction won't be affected, but it's going to speed up. So let's say a moment in time later, its new velocity vector will be something like this. It's bigger than the old velocity vector because it's traveling faster now. So the velocity vector changed. It used to be described by this arrow, and now it's described by this arrow. So there was a change in the velocity. Notice the velocity changed from here to here. So that blue arrow that I just drew represents the change in the velocity. So notice that the force caused a change in the velocity, and the direction of the force and the direction of change of the velocity were the same. Let's look at another example. Here's a particle traveling with some initial speed v naught to the right. Let's imagine I apply a force opposite to the way it's currently moving. Now we've already seen that that's going to cause the object to slow down. So a moment later in time, it's still moving to the right, but at a slower speed. So there's its new speed. I labeled it v1. So the velocity vectors changed again. It went from here to here. Or in other words, this blue arrow shows you the change in the direction of change of the velocity vector. So notice that this blue arrow is in the same direction as the force. In other words, the force caused a change in the velocity. And the direction of the force and the direction of the change in the velocity, or the direction of the acceleration, they're the same. One more example. Here's a particle traveling to the right with some initial speed v naught. Now I apply a force F, and this force happens to be perpendicular to the motion. Okay? So we know that that's going to change the velocity. We know it's not going to change the speed, how fast the particle is going, but it is going to change the direction of motion. So if the particle is initially moving to the right, then a moment later, it's going to be moving, it's going to follow a curved path, so a moment later, its velocity vector might look something like this. It's bent up slightly, owing to this force. So let me put these two velocity vectors tail to tail so I can compare them. And notice that if I look at the change in the velocity, it went from here to here. So the change in the velocity is described by that upward blue arrow. So that blue arrow is the change in the velocity. Notice it's in the same direction as the force. So in all these cases, we see that the change in the object's velocity is in the same direction as the force, or said differently, the object's acceleration, and acceleration just means the rate of change of velocity, the object's acceleration is always in the same direction as the force acting on the object. The next key concept is the notion that the bigger or larger the force on an object, the more rapidly its velocity is going to change. That should make sense. We've seen that forces affect motion. They change an object's velocity. And if you apply a big force, you'd expect that the change in the velocity is going to occur more rapidly. And in fact, it's directly proportional. It turns out that if you push twice as hard, whatever change occurs in the velocity, in the speed or the direction, it's going to occur twice as fast if you double the force. If you triple the force, the change is going to happen 3 times as fast. So let's check your understanding here. Suppose I'm looking at two identical particles, particle A and particle B, and they're moving along, and there's a force acting on each particle. And I want you to look at these pictures here and determine on which particle there's a larger force that's acting. So what these pictures are showing you is that the particle A is initially here, but there's some force that's acting on it, and let's say a second later it's here, a second later it's here, a second later it's here. Likewise for particle B. It's here, a second later it's here, a second later it's here, and so on. which of these two particles has the larger force acting on it? I'd like you to pause the tape here so you can spend a few moments on your own just pondering this. Okay, so let's look at this situation again. Now, the final answer here is that the force on particle A is larger than the force on particle B. Particle A experiences the larger force. Now, that may be obvious to you. It may not be obvious to you. If you look at the spacing, you see that this is showing you where the particle is, and then where it is a second later, and so on. So it's clear that particle B is traveling faster than particle A. After all, in 1 second, particle A goes from here to here. But in 1 second, particle B goes from here all the way to there. So particle B is traveling faster. But how do you determine forces? Forces change the object's velocity. And the larger the force, the more rapid the change is occurring. Okay, so let's look at particle B. Okay, it's moving along to the right at some speed. And if you look at the spacing between where the particle is at different moments in time, you see how it's gaining speed. So particle B is going faster and faster and faster. It's gaining speed, but it's kind of not gaining speed very rapidly. So it's going a certain speed, gaining more speed, gaining more speed. But look at particle A. It starts out going pretty slow, but then it goes much faster, and now it's going much faster than before. It's gaining speed very, very rapidly. So both particles are experiencing a change in velocity, but particle A is experiencing a more rapid change in velocity. Therefore, particle A has the larger force acting on it. Let me give you a second test of your understanding. Suppose I have a particle, here it is, and it's going to move through space, and it's going to travel along this curved path at a constant speed. Okay, so picture a particle moving along at constant speed, traveling along here. And it's going to pass by point 1, and it's going to pass by point 2. There's a force acting on it when it's at point 1, and there's a force acting on it when it's at point 2. And I want you to determine which force is going to be larger. So spend a moment or two thinking about this question. I suggest you pause the tape. Okay, so let's address this issue. We have the particle traveling at constant speed along here. We want to know, is the force that's acting on it at point 1 bigger or smaller compared to the force that's acting on it at point 2? Now, first of all, you should ask, how do we know there's a force acting on it at point 1 and at point 2? Well, the speed isn't changing, but notice that the direction of motion is changing. The particle is going along a curved path here, so there's got to be a force. Likewise, when the particle is going around point 2, it's bending, its path is changing. Forces affect the motion. They either speed it up, slow it down, or they change the direction of motion. And in this case, the direction of motion is being affected, so there must be a force acting on the particles here. And in fact, because the speed of the particle isn't changing at point 1, then any force that's acting on it must be perpendicular to the motion. Same thing at point 2. Any force acting on it must be perpendicular to the motion, since it's not speeding it up or slowing it down. So the force that's acting on at point 1 here, okay, so here's the particle, it's coming along, and right at that moment there, it's traveling in this direction. So V0 represents the speed of the particle at that point. Because the path or the direction of motion is changing, that means there must be a force on it perpendicular to the motion. So here's the force acting on it, perpendicular to the motion, and that force is causing it to go around this bend. But notice that when it goes around near point 2, it's going around this sharper bend, so the direction of motion is changing more rapidly. So again, like right at this point, at point 2, the particle's moving this way. There's got to be a force on it that's causing its path to be bent, and so that force is perpendicular to the motion. Here it is. But it's got to be larger than this force because this bending is occurring more rapidly than this bending. This is a shallow bend, and this is a sharp bend. This perhaps isn't surprising. I mean, imagine if this is you driving in your car, and you're going around a curved path, and you're going always at, let's say, 30 miles an hour. So here you are traveling along at 30 miles an hour, and here you're going around a shallow bend. Well, if it's shallow enough, you don't really notice that very much. But if you're going around this really sharp bend at the same speed, you're really going to notice that. So your body is able to sense the acceleration or the force, and it's much stronger in this case than in that case. So the take-home point with both of these examples is that if you want to understand the forces, you don't look at just the velocity, you look at how the velocity is changing, because that's what forces do. They change the velocity. So now we're in a position to return to that warm-up problem that I gave you a little bit earlier. Namely, you were watching a particle moving along a curved path here. The dots are showing you the particle's position at equally spaced moments in time. And what I want you to do is, at the indicated points, here and here and here and so on, I want you to draw the direction of the force acting on the particle. Don't worry about the size of the force, just get the direction of the force. Use what you've learned about how forces affect motion to draw the direction of the force at each of these points. At this point, you should definitely pause the videotape and give yourself a few minutes to attempt this problem. Go for it. Okay, you're back. So now let's look at this problem again. In this region here, I claim that there's no net force on the object. Why? Because this particle is moving along a straight line. It's not bending. And because these points, these dots here, are equally spaced, that means the particle isn't speeding up or slowing down. It's traveling at constant speed. So if a particle travels at constant speed, no change in speed, and no change in direction, it's just moving in a straight line, that means there's no force acting on it. Now look over here. If you look at the dots, first of all, you see that the particle is still moving in a straight line to the right. Okay. But notice that the dot spacing is changing. See how it's increasing? That means the particle is going faster and faster and faster. So the particle's speeding up. So that means there must be a net force to the right on the particle in this region. Let's look over here. The particle's still moving in a straight line in this region, but you see how the spacing between the dots is decreasing. That means the particle's slowing down. So we've seen that that means there must be a force opposite to the direction that the particle's moving. Now let's look in this region here. You see that the particle is going along a curved path. So there's definitely a force on it. But notice that that force must be perpendicular to the motion because the particle, these dots are equally spaced. That means the particle's speed isn't changing as it goes along here. So the particle is traveling at constant speed along this curve. So therefore, if the particle at this point right there is moving with some velocity v in that direction, right at that moment in time, then the force must be perpendicular to the motion, because perpendicular motion forces change the path, they curve the path, but they don't change the speed. Let's look at this point right here. At this point right there, the particle is moving along, but it's going around this curved path. The particle's speed isn't changing because these dots are equally spaced. So again, the force must be perpendicular to the motion. So right at this point, the particle is moving with speed v in that direction. So the force must be perpendicular to the motion. Finally, let's go to that point right there. Now this thing is a little bit trickier to think about because two things are happening simultaneously. First of all, look at the spacing of the dots. You see how it's moderate size here and then gets really large here? So that means as the particle is going around this curve, it's speeding up. So it's going around a curve, its path is being bent, and at the same time it's speeding up. So what does that mean? So right at this point, the particle is moving in this direction. So I've just indicated that it's traveling with some speed v right at that moment. Okay, now, because the particle is going around a curve, its path is bent, that means there must be a force perpendicular to the motion, because we've seen that perpendicular forces bend the path. So there's got to be a perpendicular force that's causing the path to bend. However, the particle is also speeding up. We've seen that forces that are parallel to the motion in the same direction that the particle is moving cause the object to speed up. So there must be a force pushing like this in the same direction that the particle is moving. That will cause it to speed up. So both of these forces, this dashed one and this dashed one, are happening simultaneously. So to get the direction of the net force, I want to add up these two force vectors. So I'm going to take this force vector and slide, whoops, do that again. I'm going to take this force vector and I'm going to slide it down, put it head to tail, and then I'm going to add the two vectors together, and that dark red vector, that's the direction of the net force acting on the particle. Next, let's turn to our next key concept. The idea here is as follows. If you have a force acting on an object, so here's a force acting on an object. If you break up that force into its x, y components, then you can effectively treat this as two separate problems. You can look at the x component of the force and figure out how that affects the motion, and then separately look at the y component of the force and figure out how that affects the motion. And in effect, you can treat these two forces as separate and independent from one another. So this is going to turn out to be a very useful thing when you're doing problem solving. You'll often want to break a force up into its horizontal and vertical components, or xy components, and then you can treat this as two separate problems, one in the x direction, one in the y direction. Now, at this point, this probably seems rather vague, and what do I mean by this? Hold off on that. We're going to see, you're going to get a taste of this a little bit later on in the tutorial, and you'll get a much bigger taste for this in your physics class itself. The next key concept is as follows, and this is a familiar one. The larger an object's mass, the harder it's going to be for a force to change the object's velocity. This is probably pretty familiar to you. If you push on something that's very massive compared to push on something that isn't massive, it's kind of easier to affect the motion of the less massive object. Okay? And in fact, it turns out that the rate of change of the object's velocity, in other words, the object's acceleration, is inversely proportional to the object's mass. Okay? So the more massive it is, the rate of change of the object's velocity, in other words, its acceleration, is going to be less. So here's just a visualization of that. Here I have two objects. This one is supposed to be more massive than this one. So here's a smaller mass, larger mass. We're pushing on them with the same strength force. Okay, so the force is going to affect the motion, and so what's going to happen is that this object is going to start accelerating. Its velocity is going to change. So we can see that as we push on it. Here's where it is at a later time, and then at a later time it's here. You see how its velocity is changing very rapidly? Compare here to here, its velocity is growing very rapidly. On the other hand, when you are pushed with that same force on this more massive object, yes, it's going to move to the right and its velocity is going to increase. See how it's moving faster and faster and faster. But it's taking its time building up speed. The change is happening, the change in velocity is occurring, but more slowly. It's less rapid of a change. You're probably familiar with this concept in another way. Suppose I gave you two objects that were very similar in mass. And in fact, you might want to test this out yourself. Go to your room and find two objects that are very close in mass to one another. And suppose I say, I want you to judge which of these two objects is more massive. So go ahead and do that. You might want to pause the tape and go ahead and hold it in your hands and judge. And look what you're doing when you're judging. Okay, if you're back, what you may have noticed is what people naturally do when you're holding two objects that are very similar in mass, but you want to tell which one's more massive, you probably wiggled your hands a little bit, up and down, up and down. And it's probably a pretty subtle motion. You're just kind of lightly pushing your hands up, moving your hands up and down. The idea is you're attempting to apply equal forces to both of these objects, and you're trying to see which one is easier to change its motion. If it's easier to change its motion, that's the less massive one. So that's what you're doing when you're holding the two objects and slightly wiggling them in your hand. You're trying to gauge which one it's harder to accelerate. Our next key concept has to do with something called the center of mass. See, very often in physics, we have some object, and it could be anything. It could be a car, a planet, a tiny little drop of water, and we're interested in looking and understanding the motion of that object. But the object itself is actually made up of many, many individual particles. After all, like a car is made up of many, many little atoms. Same thing for a planet or a drop of water. It's composed of tiny little particles. And each atom that makes up a car is moving differently. Every atom making up a planet is wiggling around, moving in some fashion. But suppose we want to know what the overall motion of an object is. So for example, suppose I take a stick and you just throw it across the room. So here's the stick traveling along here, and it's spinning as it's traveling along. And if I look at different parts of the stick, like here or here or here or here, different parts of the stick are moving differently. So the question is, if I want to know the overall motion of the stick or the overall motion of the car, not the motion of every single atom that's making up the car, how do I describe the overall motion of an object? In other words, the motion of the object as a whole. Well, the idea is going to be we're going to focus on the center of mass of the object. That's going to be the key. So let me flesh that out a little bit. The center of mass of an object, when you have an object and it's made up of many, many, many individual particles, the center of mass of the object is the point about which that mass is evenly distributed. So for example, here are three objects. Okay? Here's a disk, here's a stick, and here's a ring. And each of these objects is made up of many, many individual particles. Lots of atoms making up this disk. Lots of atoms making up the stick. Lots of atoms making up this ring. The center of mass is a point about which all the masses are evenly distributed. So in this example, the center of mass of this disk lies right there at the very center. For this stick, the center of mass lies right there. For this ring, the center of mass lies right there. It's the point in space about which the mass is evenly distributed. By the way, the center of mass of an object, there doesn't actually have to be any mass there. Like in this ring, all the mass is in this ring. There's no mass here in the hollow part, but nonetheless the center of mass, this special point that we're going to focus on, is there, right at the center. Now, if I gave you a more complicated shaped object, it may not be so easy for you to figure out where the center of mass of that object is, but every object has a center of mass, and you'll learn later on in your physics course how to find it. The point for now is that every object has its center of mass, and the center of mass is going to be the key to describing the overall motion of the object, because we're just going to follow the motion of the center of mass. So here's and this is a truly remarkable result. When a force acts on an object, so if you have a car or a disk or a stick or a planet, and there's some force that's pushing on it, then the center of mass of the object will move as though the whole object were just a point particle subject to that same force. Let me illustrate what I mean by this. Okay, let's say I have just a particle. There's a single particle, and I apply a force to the right. So the particle is going to start accelerating to the right. So there it is. It's going to move right, and it's going to go faster and faster and faster. Okay? So that's the case of a force applied to a particle. Straightforward. But now suppose I apply that same force not to just a single particle, but to an extended object, like a stick, where the stick is made up of many, many individual pieces, individual atoms. How is it going to move? Okay? Well, I want you to imagine that, for the sake of argument, that this stick, the total mass of this stick, is the same as the mass of that particle that we considered previously. Okay? So what's going to happen is, here's a stick, you push on it with that same force, and it's going to start moving to the right. And it's going to go faster and faster and faster, like that. Okay? If that seems plausible to you, I want you now to focus on the center of mass of the stick. And you see how the center of mass of the stick is moving just as though it were a particle. So you might say, okay, yep, that seems reasonable. Okay, so the point here is, when you have an object and you apply a force to it and you want to know how the object moves overall, just focus on the center of mass of the object and how that moves. Don't worry about what this part of the stick is doing, or that part of the stick, or that part. Just focus on the center of mass. Now, this may seem pretty plausible and reasonable. So why did I call this a remarkable result? Well, let's say I took that same stick, but this time I applied a force that wasn't aimed right at the center, but it was off-center, like near the top. Now imagine pushing on a stick like that. The stick is going to move. You're pushing on it to the right, so the stick's going to move to the right, but you see how it's also going to start spinning or rotating as it moves. So a moment later it might look like that. A moment later it might look like that. A moment later it might look like that. So it's not only moving to the right, but it's also spinning. But again, if we just focus on the center of mass of the object, you'll see that the center of mass moves just as though it were a point particle subject to that same force. So here's the bottom line. You can have an object. It could be a funny shaped object, it could be a car, whatever it is, and if you apply a force to it and you want to know how it moves, just focus on the center of mass of that object and the motion of the center of mass, because it will behave just as though it were a point particle and you were applying a force to that same point particle. Okay. So, once again, any time in your physics course when someone talks about the overall motion of an object, where the object's made up of many, many individual atoms, you really mean the motion of its center of mass. Okay, so let's summarize and synthesize what we've discovered so far. First, a net force on a particle is going to cause that particle to accelerate. And remember, acceleration means that the particle's velocity is going to change. And velocity means the speed and direction. So when you apply a force, the speed and or the direction of the particle, namely its velocity, is going to change. That's what forces do. When you think of a force, think of it as a push or pull, and what does it do? It changes the velocity. Second, the rate at which the velocity changes, we call that the acceleration. Anytime the velocity of an object changes, we say it's accelerating. And mathematically, if you're taking a calculus-based physics class, you'll see that written as the acceleration vector is the rate of change or the derivative of the velocity. But intuitively, just think that the acceleration describes the rate at which the velocity is changing. And velocities change because there's a force on an object. Third, forces cause accelerations, and the direction of the force on an object determines the direction of its acceleration. The direction of the acceleration is always the same as the direction of the force that you're applying to that object. Fourth, the larger the force, the larger the push or pull that you're exerting on an object, the larger the resulting acceleration. In other words, the more quickly the velocity is going to change. The larger the object's mass, the harder it is for a force to accelerate it. In other words, the more the velocity is going to change, but it's going to change more slowly than it would for a lighter mass. Accelerations and masses are inversely related. For a given force, the smaller the mass, the larger the acceleration. If we put this all together, we arrive at a truly amazing result. This is a fundamental discovery known as Newton's second law. It says that the acceleration of an object, that means the rate at which its velocity is changing, depends on the force acting on it divided by its mass. So the rate of an object's change in velocity is determined by the force acting on it divided by its mass. So you apply the force, and this expression tells you what the resulting acceleration is going to be. This is one of the most famous laws in physics, and it's often written in a slightly different form. Namely, sometimes you'll multiply both sides of the equation by m, and we write this as F equals ma. And the way to interpret this, don't think of this as saying a force equals or is the same thing as a mass times an acceleration. The way you should think about this intuitively is that when you apply a force to an object, the object is going to respond by changing its velocity, by accelerating. So you apply a force, and the result is that the object begins to accelerate, and this tells you the relationship between the force that you applied and the resulting acceleration. Again, don't think of this as saying a force is a mass times an acceleration. There is no force in nature called ma. There's a force in nature called gravity, there's a force in nature called the frictional force, and so on. There is no force in nature called ma. Rather, this is telling you what forces do. Forces acting on objects produce accelerations, and this relationship tells you the size of the acceleration given the force. So once again, this is probably one of the most fundamental principles that you're going to encounter in your physics courses. A force produces an acceleration. By the way, the acceleration that appears here, when you apply a force to an object, the object accelerates. That means the object's velocity is changing, and the acceleration refers to the acceleration of the center of mass of the object. Remember, when you have an object made of many particles, you always focus on the motion of its center of mass. So this acceleration refers to how that center of mass of the object is going to, its velocity is going to change. So what I'd like you to do now is attempt the practice exercises associated with this part of the tutorial.